Hi everyone, we are Group A, and the topic of our final project is building an optimized volleyball tournament schedule using operations research techniques. Traditionally, the NTU volleyball tournament is scheduled manually. This meant it was time-consuming, error-prone, and lacked any optimization. It depends heavily on human labor, which isn't scalable or consistent. For example, organizers might accidentally assign a referee to a match on a day when they are actually unavailable. Mistakes like this can lead to unnecessary disputes, or even last-minute rescheduling or cancellation. Therefore, we want to build a smart system that can automate data handling, support grouping logic while avoiding bias, and most importantly, generate a schedule that's optimized to save time and effort. We want to address the challenge of scheduling a departmental volleyball tournament. The tournament uses a round-robin format in which every team in a group must play against all other teams in the same group. Our goal is to complete all group stage matches in the shortest possible time, minimizing the total number of days needed to finish the tournament. For the parameters, our model takes several things into account. First, we consider team availability. Each team has specific weekdays when they can play. Second, we include referee availability and conflict information. Referees can only work on certain days, and they are not allowed to officiate matches involving their own department to avoid conflicts of interest. Third, we account for the number of courts available each day. Since it's limited, it adds a real-world constraint to the schedule. We also categorize teams into 4 tiers, based on skill level, which help balance the competition within groups. Finally, each team is assigned to a group and must play all other teams in their group once, following the round-robin format. Now for the constraints. These are the rules our schedule must follow. First, matches can only happen on days when both teams are available. Next, referees must be available and they can't be assigned to more than one match per day. We also enforce conflict of interest rules, meaning a referee cannot officiate matches that involve teams from their own department. To protect player health and fairness, each team can only play once per day, and at most twice per week. And lastly, to maintain competitive balance, no group is allowed to have 2 teams from the same tier. We use the data from the tournament held in 2025 spring, which is this semester's tournament. The spreadsheet includes information about teams and referees, as well as their availability and group assignment. The spreadsheet is restructured. In this example, we use binary data form to present the referee's availability. Now let's move on to our model formulation. We divide our formulation into 3 phases. Phase 1, we define the problems and introduce variables. For Phase 2, we build the model with constraints that reflect reality. And lastly, for Phase 3, we prepare for computation and design algorithm. Let's start with the sets we use in our model. This defines the different elements involved in our scheduling problem. These sets build the foundation of our model by defining what we are scheduling and when and where it's allowed. Next, we define the fixed input parameters used in the model. These parameters are based on real-world inputs, like team schedules and referee preference. Now let's look at the decision variables, the things our model is trying to determine. These are what we are solving for. Who plays who and when, where, and who is the referees, while also keeping the tournament short and fair. Our goal is to minimize the overall cost of the schedule. The objective function includes three main parts. First, we minimize the max span, or the total number of days needed to complete the tournament. Second, we penalize assigning referees on days when they are only partially available. We apply a weight of 0.1 to discourage that unless necessary. Third, we minimize workload imbalance across referees. We use deviation variables to keep referee duties as evenly spread as possible, and assign a small penalty of 0.01 per deviation unit. We also define delta as an indicator. It equals 1 when a referee is semi-available, and 0 otherwise. These first constraints make sure that every match in the round-robin schedule happens once and only once. It must be assigned to a specific day, court, and referee. The second constraint ensures that every field is used for only one match per day, so we don't double book courts. This constraint says that each referee can only officiate one match per day. This avoids overloading any individual referee. And this one makes sure that no team is scheduled for more than one game on the same day. Next, we have constraints that account for conflicts and availability. This condition ensures that referees don't judge games involving teams from their own department. If a conflict exists between a referee and a group, they are not allowed to officiate any of that group's matches. The respect availability checks if both teams and referee are available on a certain day. If either team isn't available or the referee is not available, the match cannot be scheduled. The constraint define max spans helps us check the max span, which is the last day of match is scheduled. We want to minimize this as part of our objective. We also count how many matches each referee is assigned to in total. This will be used in balance the workload. Finally, we check how far each referee's workload is from the average. This let us penalize unbalanced workloads in the objective function and encourage fairness. Now we are ready for algorithm design and solving the integer program. So this photo shows a generated referee conflict table. This makes sure referees don't officiate matches involving teams from their own department group. If a referee is eligible to referee a group, we mark that as 1, meaning they can officiate. If not, we mark it as 0. And if a referee's department has both an A and a B team, we assume they belong to the A team and they are restricted from refereeing games from either A or B's group. Now let's start with our baseline, the naive scheduling approach. This method is straightforward. It goes group by group, match by match, and tries to schedule each as early as possible without any form of optimization. For each day, it checks whether both teams are available, whether they already have a match that day, and whether they hit the weekly match limit. If all good, it finds a referee who's available and not conflict with the group, then picks the one who's done the fewest matches so far. Courts are assigned based on availability, and once a match is scheduled, it updates all internal checking, like team schedules and referee workloads. However, since this method doesn't look ahead or backtrack, it can leave a lot of matches unscheduled, especially under tight constraints. To improve on this, we designed a heuristic algorithm. It's still greedy, but smarter. It builds the schedule one match at a time, starting with Group A and moving forward. What makes it better? First, it's flexible with referees. If no referee with full availability is free, it considers those with partial availability too. That helps reduce unscheduled matches. Second, it balances referee workloads better. We always choose the referee who has officiated the fewest matches so far, regardless of availability level. Third, it has smarter date-skipping logic. If nothing can be scheduled on a day, it moves on, rather than wasting time. Lastly, it enforces more constraints. It avoids duplicate matchups, enforces weekly team limits, and generates cleaner and more realistic schedules. So what exactly did we change from naive version? We added partial referee availability handling. We added workload-based referee assignment. We let the scheduler skip days, and we tightened constraints to avoid messy output. These small improvements added up to big performance gains. To measure performance, we used a combined objective value. This includes the tournament duration, or maxspan, penalties for constraint violations, like assigning semi-available referees, and referee workload imbalance. We want fair distribution. We calculated optimality gap by comparing heuristic and naive results to the optimal solution from Group B. Let's look at how our heuristic compares to the optimal solution. In cases 1 through 3, the gap was under 10%, which is great. In the harder cases 4 and 5, the gap was higher, around 24 and 51%, but the schedules were still feasible and completed on time. This shows that our heuristic is both effective and robust, especially when things get tricky. Now let's talk about the naive method. These are the optimality gaps from naive versus optimal. For case 1, it is 265% worse, and for case 4, it's over 400% worse. Across all 5 cases, the heuristic obviously outperforms naive scheduling. It reduces missed matches, shortens the tournament, and distributes workload more fairly. So, in conclusion, we tackled a tough problem: how to schedule a departmental volleyball tournament fairly and efficiently. We built a solid optimization model with real-life constraints, like team availability, court limits, and referee conflicts. Then, we created both naive and heuristic algorithms to test our ideas. Although we didn't factor in unpredictable things like whether our schedule is tight and clean, leaving space for real-world adjustments. Most importantly, our heuristic offers a great trade-off. It's fast, easy to implement, and gives results close to optimal. That makes it a strong solution for practical use. Now, let's bring our solution to life. On the right side, you can see the user interface of our system. We start by clicking the Select File button to upload an Excel file that contains referee department information and team tier data. Then, we enter the start date, which indicates the earliest possible match day. Once that's done, we click Generate Groupings and Conflict Table to move to the next step. In the second phase, we upload the files that were generated in the previous step, the groupings and the referee conflict table. Next, we upload an Excel file containing the referee's availability and the team's availability. Once both files are uploaded, we simply click Generate Schedule, and the system handles the rest. After processing, the result is available in the download area. You can download the full schedule as an Excel file to make it more intuitive. The system also displays the schedule directly on the interface, including the date, field, home team, away team, and the referee. One highlight of our system is the calendar mode. It gives a clear visual of all the matches happening on each day, across all 4 fields. Using the search bar at the top, we can easily check the schedule of a specific referee, including all the days they are assigned to officiate. We can also look up a team to find all the dates and opponents they are scheduled to play against. And finally, we can search by specific date to see all the matches scheduled on that day. Our interface is designed to be simple, intuitive, and user-friendly. With our system, competition scheduling is no longer a hassle. Thank you all for listening. We hope you enjoyed our presentation.